name is Matheus Rui. I'm from Brazil. I'm doing a PhD at Federal University of Santa Catarina. And the title of my talk today is Belief in Credence, Bringing Doxastic Logic and Probability Theory. I'm not a logician, I am an epistemologist, more precisely a formal epistemologist, a Bayesian, and something like that. And we will talk about these stuff here. So, very briefly, I will begin by introducing these notions of belief in credence, what I'm talking about, and present some postulates for some formal rational postulates for belief and credence. And after that, we'll see how can we relate these two notions, assuming it's rational, they're rational postulates. And finally, we'll see how can we interpret and expand this discussion in a diachronic way by means of belief revision and so on. So let's start. Beginning, I need to make clear what I'm talking about and what is belief and what is credence. In a very short way, belief is a qualitative notion, also can be recognized as a form of acceptance. I will not do any distinction precisely details here and so on. It's the basic idea that Bayesians can believe in P or he doesn't believe in P. P is a proposition and so on. Belief is used mainstreaming theory of knowledge, philosophy of mind, philosophy of language. It's a very philosophical notion of belief. Usually we assume that belief rationality has a kind of logical structure. What I'm calling here doxastic logic is some kind of logic, general logic for qualitative states. I'm not talking about precisely doxastic logic, indicas doxastic logic, as we'll see soon. On the other hand, credence, or also degrees of belief, or also subjective probability, is a quantitative notion. Can be measured in a degree of strength between 0 and 1. And credence use is mainstream in Bayesian theory, rational choice theory, and Bayesian confirmation theory in philosophy of science. And it's generally assumed that credence rationality is guided by probability theory, classical probability theory. Some here very basic stuffs for belief. Here Bell means belief, and W, all possible words, that means a logical proposition, very basic stuffs. Shortly, belief must be closed under logical entailment. In a synchronic perspective, this is what just I'm assuming, logical entailment for belief. For credence, like a Bayesian, and I need to assume that I'm a Bayesian guy, I'm assuming probabilistic axioms, Kolmogorov probabilistic axioms. The three axioms and the definition of conditional probability. Nothing strange, everything is happening in a normal way until here. Now, given that, my talk will be about how can we connect these two notions and their postulates. The most intuitive answer is say that belief is some kind of high confidence. For example, I believe that the sun will rise tomorrow if I'm high confidence of it. More precisely, we can say that the agent rational believes about a proposition if and only if its subject probability, the credence in A, is greater than some threshold between 1/2 and 1. This idea was first proposed by Richard Foley. He has received the name of Lockean thesis. Doesn't matter here the historical facts about Lockean, etc. And this is the Lockean thesis. The problem here is establishing the threshold. The problem is that when the threshold is established below, strictly below 1, and this is a non-skeptical requirement, locking thesis, given our postulates, earlier postulates for credence and belief, is inconsistent, implies a contradictory set of belief. And the main argument for that is probably well known by most of you, the famous Lother paradox. I'm not go deeply here, but just assume a locking threshold of 0.9, assume a small lottery, think about a small lottery with 100 tickets. So for the probability distribution is equal between the tickets, and so by locking thesis you are entitled to believe that each ticket will lose because the probability of a loser ticket is 0.99. But we know that the lottery is fair. That means that at least one ticket will win. So since by locking thesis we are justified in belief that each ticket will lose, and at the same time we know that the lottery is fair, putting all things together with the postulates for rational belief, we can construct conjunctions of beliefs. By Morgan's law, we end up with a contradictory set. I think that is very common for most of you also. Now I want to interpret that problem in a small different way, and an interesting one. I want to interpret the locking thesis and the other solutions and the Lother paradox in a geometrical form. Beginning, since logic has a discrete structure and probability a continuous one, we can interpret the connection, one connection between logic and probability in a geometrical form. For example, here in the figure, as you can see, the endpoints of the line represents proposition A and its negation. The continuous line represents all possible probability distribution. There are infinite, uncountable probability distributions in the line within the unity interval. And the acceptance region of locking thesis here is represented with the threshold S of 0.75. We can extend that discussion in a case with 3 propositions. Try example with 3 propositions in a partition. That means that they are collectively exhaustive and mutually exclusive. Expanding the line in a triangle, we have this figure. In figure A, the triangle base worked as a unity interval between A and C. That was the line from the last chapter, the last slide. The same happens with each of triangle's edge. In figure B, the black dotted line represents the locking threshold S for reject each proposition in its opposite side. So, for example, this dotted line represents the region. I can print color all this zone represents the acceptance zone for a probability distribution of the negation of the proposition B. And the point in the center of the triangle is the probability distribution of where all of the 3 have the same probability 1/3. And here the perpendicular red line in red, opposite to the vertex A, is the measure of the probability of A. That means that here probability A is 1, and here probability of A is 0. Now we can look at closely to the Lother paradox and the Lother paradox and the locking thesis in a geometrical way. The dark gray region represents the acceptance zone for the respective strongest proposition. The light gray regions represents the acceptance zone for disjunctive disjunctive propositions. For example, here, A or B, is equivalent, given our partition, to C. And the white central region represents the acceptance zone, where the probability distribution P implies acceptance just for the sure proposition, the tautological one, A or B or C. Uninformative proposition. Inasmuch as the threshold value, and this is the interesting part, inasmuch as the threshold values goes down, here is a measure of the threshold, the black here is 2/3. So inasmuch as the threshold value goes down, the acceptance zone become more thicker. And when the threshold is below 2/3, the dark gray areas collapse into each other, and a contradiction is accepted in the center of the triangle. So a distribution, a probability distribution in that zone is a contradictory one. This is why Lottery paradox implies a contradictory set of belief. Now we will look for some other attempts to bridge belief and credence, different from the Lockean thesis, and how can we interpret its geometrical form in the same way. The first one that I show here is the probological theory. While Lockean thesis takes into account absolute probabilities, probological theory considers the odds between propositions. And these guys, Lin and Kelly, are the main responsible for bringing that geometrical discussion to the problem. And they proposed this theory, also known as geological theory or also tracking theory. And here basically, being W a complete answer to a question, and W is just a word belonging to a proposition. A probological theory says that you must reject some answer to a question if and only if the ratio between that answer and its most probable contender it's below some threshold. This rationale gives rise to the odds. This is why they consider the odds between propositions. You should not worry. About how to precisely comprehend this. You can just trust me, for the sake of the argument, that this theory, like this formula, gives rise to the following geometrical form. In theory A, we can see that the zone for acceptance when the odds threshold is equal to 1. There is here the acceptance zone don't collapse into each other, and there is no zone for accept a contradictory set of proposition in probological theory. In theory B, the odds threshold is equal to 3. The highlighted red line is an example of constant odds line, and this line gives rise to this geometrical aspect of camera shutter aspects of this theory. Precisely in the red line, all probability distributions ensures the odds of 3 to 1 for probability A against probability B, both related to probability C. So all probability distribution below the red line is a probability distribution that favors A against B. Given that, we now can look briefly at another attempt to connect to belief and credence, a different one, and that is the human thesis proposed by Leitgeb. For him, it's rational to believe in a proposition only in case that is rational to assign stably high credence to it. And stability here means that the probability of each proposition conditionalized by an extended possibility, and here the letter Y is a member of this set Y of extended possibilities, must be sufficiently high. Again, you should not worry about how to comprehend precisely this, because we will check how this gives rise to a geometrical interpretation. In figure A, we see that human threshold of 1/2. In that case, the only skeptical probability distribution, where the agents just accept A or B or C, is precisely the center of the triangle, where all probability distributions all propositions have probability 1/3. In figure B, we see a human threshold of 3/4. The white zone is the skeptical one. So all probability distributions inside the white zone is a skeptical probability distribution. So we can conclude some things until now about all of that. Very shortly, both probological and human theory avoids the coarse-grained lottery paradox. They are non-skeptical, that is, they admit belief without maximal probability. They are consistent. There is no zone where a contradiction is accepted. They rely on contextual parameters to establish the threshold value. But human thesis is more skeptical than probological theory with the same threshold. As you can check, the white zone here is bigger than here. So human thesis is a more skeptical one, given the same equivalent threshold. Now I will address all of this in a dynamic perspective, being closer to the workshop theme. We need to ask now what happens when some new information is learned? What happens when we update the belief set? And here is the geometrical interpretation of an update. All the same things apply, propositions A, B, C in a partition, and we can see in the figure that given a probability distribution P, and remember that probability distribution is any point inside the triangle, after learning not C, P, the new P, is the point here. The new probability distribution, after learning not C, is the point on the segment AB. Here in the segment AB, C has probability 0. So, the new probability distribution is the point on the segment AB that intercepts the straight line from the first P, to the corner of C, where C has probability 1. Here, C has probability 1, and in the segment AB, C has probability 0. So, after learn not C, our triangle becomes a line again, because C is no more in the set. Let's review the postulates again, refresh the postulates for our belief in credence. For credence, I presented these postulates, and we can here easily add one more, a diachronic postulate, a dynamic postulate. And this is conditionalization principle. I am here again assuming that I'm a Bayesian, and this is very commonly accepted as the mainstream way to do updates in a Bayesian way. This is the principle of conditionalization that is common to say that the old probability, the new probability after an update is exactly the old one in its conditional version. It's very common stuff. And what about the postulates for belief? What we should add here for a diachronic perspective in belief revision? In Bayesian, I'm assuming that conditionalization is mainstream, and everything is right with that, and we can accept here that there's no problem. I'm assuming the Bayesian perspective. But what we should add in the belief perspective, in the logical perspective, in a dynamic way for belief updates? Let's check again the human thesis and the probological theory in its geometrical form. Interposing them, we have this figure. Here, the yellow zone is where humans are skeptical and probological are opinionated. So the white zone is a skeptical one for both of them, but as I said, human thesis is more skeptical than probological, and the yellow zone is the most important here to compare these two theories. I'm really interested in what happens in this time little red zone. What happens in that zone? As we can see in figure, probological theory in a distribution inside the red zone accepts A and C, probological theory, while human thesis accepts only the tautological proposition in that area. What happens when we conditionalize on it? What happens when we learn, for example, not A? And here things starts to be really entertaining. When we conditionalize not A, when we learn not A and conditionalize it, human thesis works very logical. As we can check, the initial probability is A or B or C. You learn given not A, that means that you learn not A, we just end up with B or C. Very logical. But probological theory works in a different way. The initial belief in this red zone is A or C, that equals to not B in our partition, because B or C is equivalent to not B. Given not A, we ends up with B or C, or that means that B appears again, B return to our set. Not B was accepted, and we learn not A. Now B return to the set. In a disjunctive way, but B is no more excluded here. So probological theory doesn't look very logical as we understand. Because probological theory doesn't comply with this principle of inclusion plus preservation that is based on axioms 3 and 4 for revision in AGM theory. That means that if proposition A is consistent with what the agents believe, then the B is a consequence after the belief set revised by A, if and only if B is a logical consequence of the initial belief set together with the proposition A, and we just close it under logical entailment. Cn here means logical consequence, and so B is a consequence of this. Shortly, here we just add A to the set. This is why it's called preservation and inclusion. We just add A to the set, and everything is fine. So probological theory doesn't comply with this rule. Inclusion plus preservation is a logical consequence of one most famous principle of rational monotonicity. This is the main responsible for making in a non-monotonic logic a preferential model in semantics. Rational monotonicity makes a preferential model in non-monotonic semantics a totally ordered one instead of a partially ordered one. And here just some clarifications. We can define this Bell operator in a revision in AGN terms and in non-monotonic operator. We can conclude now that the model for belief revision in human theory, the qualitative model, is AGN theory. The model for belief revision in probological theory is preferential model in Schopen semantics for non-monotonic logic. AGN theory satisfies rational monotonicity, while non-monotonic preferential logic models don't satisfy. But what are the key contents for each of them? Each side, how they argue for their theories. According to Lin Kelly, a model of the guys from probological theory, a model of belief revision that satisfies rational monotonicity cannot track Bayesian conditionalization. And this is an important point. This means that a belief set generated by some probability distribution P, this is a belief set generated by P, any probability distribution, when conditionalized in a qualitative way by some evidence E, must be exactly the same as the belief set generated by the conditionalization probability distribution P given E. And that this is tracking conditionalization. But on the other hand, Leitgeb, the guy from human thesis, according to him, a model of belief revision that doesn't satisfy rational monotonicity cannot give rise to stable sets of belief. And this respects the following tenacity principle. A true hypothesis, once accepted, is not subsequently rejected on the basis of true evidence. So concluding, finally, both models, probological and human, are well developed and avoid a great amount of traditional epistemological problems. And both can offer some insights into AGM theory and non-monotonic logics about how they related to Bayesianism and Bayesian epistemology. And now, what I'm working now currently in the last chapter of my thesis is that the disagreement must be solved by the disagreement between probological theory and human thesis must be solved by looking for an outside issue, not a formal specific issue between these theories. And that outside issue can be summarized with the following question. What is more important? Reduce belief to credence, what probological theory do in a good way, because probological theory tracks conditionalization, or comply with stability requirements for belief, what AGM theory, by consequence, human thesis do very well. So, thank you for your attention.